of the positron, the positive electron. Now, cloud chamber, metal plate in the middle here, and a trap. These early photographs are not very easy to reproduce, but if you look carefully, you can see a track coming up here with a small curvature, almost straight, and then with a greater curvature. Agree? Smaller range. And that shows that this particle was moving upwards. And for other reasons, was shown to be an electron, a very common particle. And for the direction of the magnetic field, this indicated that it was positively charged. It shouldn't have been, it should have been negatively charged. It wasn't, it was positive. Anderson, American, brilliant experimentalist, superb technique, cracked the code, and that gave the first unambiguous evidence for antimatter. Now, in fact, the theorists, Dirac, fellow of this society here, had about the same, well, a little before that, predicted antimatter. But Anderson didn't know about the prediction. And he's written that it had no effect. He didn't know about it, he wasn't influenced by it. This dichotomy between experiment and theory, this argument, who was first? Was it predicted and then observed, or observed and then explained theoretically? It's been around all the time, no doubt will continue. Blackett, here we go again, told me once, he had observed one of these tracks. It was coming down in his case. High energy, low energy. And when he worked out its sign, he found it was the opposite to what it should be. What did he conclude? He concluded that the technician had changed the direction of the magnetic field. Only known to him. Because they did that every day to sort of neutralize, make corrections for turbulence, distortion. Tragic to miss it, in a sense. But Blackett went on to get the Nobel Prize for other work involving the triggering of cloud chambers by the Geiger counter systems that were in use. Another discovery, incidentally, this business of antimatter is still with us. It is almost certain that in the Big Bang there was equality of matter and antimatter. But nowadays, we're all essentially matter. The amount of antimatter is minute. Where the heck has it all gone to? Well, it went in annihilation with matter to produce radiation, which we'll come to later. And there's a bit left over, and that's us, that's the matter, 1 part in a billion. But why was it not all annihilated? There's something fishy about the distinction between matter and antimatter, and it's still not resolved. It's one of the big problems, along with dark energy and dark matter, which we'll come to. Anyway, in the 30s, the muon was discovered. A particle intimate of mass in between that of the electron and the proton. And it's the muons that get to ground level. And there are about 5 a second passing through our heads this very minute. People with big heads, and rather more. Why does the muon exist? Has a mass of 207 times the mass of the electron. We still don't know. Very famous scientist said, the muon, who ordered that? And it's true. I spent 20 odd years trying to find anomalies in their behavior. Couldn't find any. They just behave like heavy electrons. this whole world of elementary particle physics is still full of question marks. The Higgs, we'll talk about that later if you wish, is perhaps, well, I think it is a step forward in understanding some aspects of it. But anyway, Madame Curie and others would have been very pleased about this, because this shows a cosmic ray muon coming down here. It loses a lot of energy in this metal plate, so the ray just gets through. Produces a lot of ionization, a lot of droplets as it comes down here because it's almost stationary. And then, fine, out comes an electron. Have you heard of Kandinsky, famous impressionist painter? Kandinsky? Oh, that. Far more people know these artistic things than scientific. Apparently, Kandinsky, in the 1890s, was a member of staff in the law department in Moscow City University, an amateur painter. And when the early work of Curie and other Becquerel and so on was done, which showed, like this in a sense, that material could change, matter could change from one form to another, he was amazed. Matter can change. And apparently this knocked him for 6. He gave up the university work. Very sound, I wish I had done it. But anyway, and he became an artist full time. And he developed this school. And when the Russian Revolution occurred, he had to leave. He went to Germany. When Hitler appeared, he had to leave. He went to France, but most of his best work was done in Germany. And as we know, his painting is absolutely brilliant and full of sort of allegories. You can imagine someone with a sort of tortured brain trying to think, or trying to express on paper what it's all about, this business of science, matter changing, and so on and so on. When I started research with Blackett, in 1948, my job was to run a cloud chamber and measure the radius of curvature of these electrons and work out the so-called energy spectrum. And we did it with colleagues, but it was too late. Anderson got there first, and he got a prize for it. Never mind, it was great fun. The British fellows, the Royal Society, who were prominent in that early period, were Powell and Blackett, whom I keep talking about. He died in 74, he died in 69. Blackett did a lot of measurements with cloud chambers, sort of things I've shown you. Powell did a lot of work with nuclear emulsions. Interesting. Blackett, left-wing socialist. He was a bit that way, but not as far as Blackett. He was a Fabian. The reason he stayed in Manchester for so long, didn't go to Cambridge, was because, I'm afraid, Cambridge weren't keen on having left-wing scientists. Whereas we Mancunians, of course, sorry. Right, let's continue. What do cosmic rays do? Well, if you were an astronaut, you'd have to have a thick cover over your head, space helmet, thicker than you would expect, the reason to just providing oxygen for you, keeping the oxygen in, to keep out the cosmic ray nuclei. And these cosmic ray nuclei penetrate quite a long way, as you can see here, into, in this case, the helmets of the Apollo astronauts. They really are dangerous. Now, to give a good idea, overview of what is going on, this is a nuclear emulsion technique. Nuclear emulsion is ordinary emulsion with extra silver bromine in it. And if you process it, you can, just like the cloud chamber, you get the tracks the trails left by the particle, a bit like high-flying aircraft. Often you can't see the aircraft, it's gone. But you can see the vapor trail. Same sort of thing here. And all the early work, and indeed the contemporary work, is to do with looking at the products of the interaction of one particle here with a nucleus and all these secondaries that come off. And this was a happy hunting ground in cosmic rays for the new elementary particles, and is now, of course, has been taken over by the big accelerators such as the one at CERN in Geneva. This turned out to be a heavy nucleus, and you can tell that because it produces lots and lots of electrons as it goes through. And that is why the heavy nuclei are so dangerous. You get one of these to the optic nerve, that would be it for your eye. Whereas at ground level, we're shielded by the atmosphere from these, but they're losing energy at such a high rate that they don't penetrate. In my youth, I and others did a lot of work in this very useful underground laboratory system called the London Underground. Because the little labs down there that we had, the ends of platform, were at different depths underground. Waterloo, 15 metres water equivalent. That is the depth in metres multiplied by the density. And you see Arsenal 35. Holborn is where we have a laboratory run by Imperial College, actually, 57. Platform 5, Piccadilly line, I remember correctly. Hampstead, they deep, 90. And by observing with nuclear emulsions at these depths, we could get some idea of the absorptive properties of these particles. How far can they go? That led, in the 1960s, to work in the Kolar goldfield in southern India, where we went down to a depth of 7,600 feet and ran an apparatus consisting of so-called neon flash tubes that rendered visible the tracks of cosmic ray particles. For two reasons we went right down there. How far do these ordinary cosmic rays extend? You know, 1 part in a billion or 1 in a million or whatever of them are fast enough to get right down there. And secondly, can we see the products of neutrinos? Neutrinos, neutral particles of very, very tiny mass, thought to be zero for a long time, but now known to be finite, no charge, penetrate almost completely the Earth. It should be possible to detect them if you go down far enough to get rid of the rubbish from the normal particles. And you can see here, this is a height of about 7 feet. You can see a series of red flashes here, here, here. A cosmic ray punched its way all the way from the surface